Hi class, welcome to video 8 for chapter 1. In this video, we're going to continue our practice with dimensional analysis, and I'm going to introduce you to problem-specific conversion factors. We're going to use problem-specific conversion factors to help us solve dosage problems. So what is a problem-specific conversion factor? A problem-specific conversion factor is some information given in a problem that has divided units. It will be basically a conversion factor that is only good for that problem. An example is if you had a word problem that said the speed limit is 25 miles per hour, you might think this 25 miles per hour could be used as a problem-specific conversion factor. So how would we write this information as a conversion factor? We could write it in two different ways. So we could write it as 25 miles over 1 hour, or 1 hour over 25 miles. The way we choose to write it, of course, is going to depend on what the problem asks for. To recognize a problem-specific conversion factor, you're looking for words like per. So, for example, milliliters dose per kilogram, or gram per mole, or mile per hour, as we did in this case, or gram per milliliter. Those are just some examples. Another way that you can recognize problem-specific conversion factors is the problem having divided units. So instead of this problem saying 25 miles per hour, it could have just been written as 25 miles divided by hours. So those are ways to recognize problem-specific conversion factors. Let's go through a problem that uses a problem-specific conversion factor. In this problem, it says if your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to walk a distance of 7,500 feet? So in this problem, we're looking for minutes, so we need minutes, a unit of time. And we're given here 7,500 feet. So we're given a unit of distance. There's another piece of information in this problem, and that is 65 meters per minute. And that allows us, or it's a problem-specific conversion factor that will take us from a unit of distance to a unit of time. So this is indeed a problem-specific conversion factor. And in order to use this problem-specific conversion factor to get to minutes, I need to convert my distance unit, or my unit of length, feet, into meters. So that's going to help me start writing my plan. So my plan is to go from feet to inches, and then I'm going to go from inches to centimeters. And then centi is just a prefix definition, and I can go from centimeters to meters. So this is a 1, 2, 3, 4 step problem. And we're going to start with our given. So 7,500 feet. So first step is going from feet to inches. I want feet on the bottom so it cancels. And inches on top. And the numerical value is taken from the equation sheet, or in this case it's on the slide, and 1 goes in front of foot, and 12 in front of inches. So that completes step 1. For step 2, we're going from inches into centimeters, and we want inches on the bottom so they cancel, and centimeters on top. We'll go ahead and put our numerical values in, and that's taken from the equation sheet. And 2.54 goes in front of centimeter, and 1 goes in front of inch. So that completes step 2. In step 3, I'm going from centimeters into meters. So centimeters goes on the bottom and meters goes on top. And how do I write this? So on your equation sheet, you'll be given a table and it'll look something like this. This is a portion of that table. And to turn this into an equality, put 1 in front of your prefix unit, so 1 in front of centimeter, and that equals blank meters, and that blank is whatever is given on the table, so 10 to the minus 2. So we'll put 1 in front of centimeter and 10 to the minus 2 in front of meter. And so now we're done with step 3. And then in our final step, we're just going from meters to minutes, and we're going to use our problem-specific conversion factor. So meters is going on the bottom, so it cancels, and minutes goes on top. And then we just copy the numerical value, and so we have 65 in front of meters, and this is an assumed 1 in front of minutes. So 65 in front of meter, and then assumed 1 in front of minute. And that completes step 4. So now we can look that our units cancel. And we have feet canceling, inches canceling, centimeters canceling, and meters canceling. And we're left with minutes, which is what we want. Then we can look at significant figures. And here we have 2 significant figures. This is exact. This is exact. It has that triple bar, which means definition. This is exact, and this has 2. So we'll round our final answer to 2 significant figures. When we punch this into our calculators, we got 35.1692 unit minute. Of course, that's unrounded. And then round to 2 significant figures, and this equals 35 minutes. In the next example, I'm going to teach you how to use problem-specific conversion factors to help you solve dosage problems. But first, I'm going to show you how to interpret dosage problems. This problem states penicillin 2 milligrams per kilogram is ordered for a child weighing 62 pounds. Penicillin is available as 0.75 milligrams per milliliter. How many milliliters must the nurse administer? So, what does this mean? I don't know. I'm kind of confused. What does this 2 milligrams per kilogram mean? What is 2 milligrams? What is milligrams of what and kilograms of what? The way that this is worded is penicillin 2 milligrams. This means 2 milligrams of penicillin. This per kilogram is kilograms of body weight. So typically when you do child dosing, it's going to be some amount of medicine per the body weight of the child so that they get exactly the right amount of medicine for their weight. So this could be reworded as 2.0 milligrams penicillin per kilogram body weight or body mass. The next thing that's a little bit confusing is this 75 milligrams per milliliter. What is the milligram referring to, and what is the milliliter referring to? Typically, when you have some kind of unit of mass per some unit of volume in a dosage problem, you're referring to a suspension. So what is a suspension? A suspension is basically you take some solid medicine, so let's write medicine here, and you dissolve it in some liquid. So you have some solid medicine dissolved in some liquid suspension, and then this is given by mouth. So what this milligrams per milliliter is referring to, let's write this down here, is 0.75 milligrams of the medicine, which is penicillin, per milliliter of that suspension. Using this information, we could reword this problem, and I already have the rewording written out on the next slide. Let's go to the next slide. So here's the problem reworded. We have 2 milligrams of penicillin per kilogram body weight is ordered for a child weighing 62 pounds. Available is 0.75 milligrams penicillin per milliliter suspension. How many milliliters of suspension must the nurse administer? So our needed unit is milliliters. And what's our given unit? Well, it appears that these are problem-specific conversion factors. They have divided units. Divided units doesn't necessarily mean you have a problem-specific conversion factor, but given this problem, these are problem-specific conversion factors. And my given unit then that I choose is the one that's not the divided unit. So we're given pounds. And we're talking about pounds of body weight. So I'm going to abbreviate body weight, BW. Let's write that up here for clarity, BW. And the milliliters I was looking for is milliliters of suspension. So let's abbreviate that big S. So we'll write a big S here for our needed unit. And then we can go ahead and abbreviate penicillin, big P. It'll just save us time in writing. So I'm given pounds of body weight, and I can go from pounds of body weight into kilograms of body weight, and that'll enable me to get to milligrams of penicillin. So we're going to convert from pounds to kilograms, and that's kilograms of, we're still talking about body weight. Then once we have kilograms of body weight, we can use this problem-specific conversion factor to convert kilograms of body weight into milligrams of penicillin. And then once we have milligrams of penicillin, we can use this problem-specific conversion factor to get to milliliters of suspension. So this is a 1, 2, 3-step problem. And we're going to start with our given. So our given is 62 pounds. And in step 1, we're going from pounds of body weight, let's put BW there, into kilograms of body weight. So pounds goes on the bottom, so it cancels. We're talking about body weight, and then kilograms of body weight. And this is just our pounds to kilogram conversion here. So we'll put 1 in front of kilogram and 2.2046 in front of pound. So that completes step 1. Step 2 in our plan is to go from kilograms of body weight into milligrams of penicillin. So this is step 2. So kilograms body weight goes on the bottom, so it cancels. And milligrams penicillin goes on top. And then we just copy the numbers in front of it. So we have 2 milligrams of penicillin. And this is an assumed 1 kilogram body weight. So that completes step 2. In step 3, we're going from milligrams of penicillin into milliliters of suspension. So milligrams of penicillin goes on the bottom, so it cancels, and milliliters of suspension goes on top. And then we just copy the numerical values in front of it, and we have 0.75 milligrams of penicillin. That goes on bottom, per an assumed 1 milliliter of suspension. We can go ahead and make sure that our units cancel. Pounds body weight cancels, kilograms body weight cancels, milligrams penicillin cancel, and we're left with milliliters of suspension. We can go ahead and take a look at significant figures. Here we have 2, here we have 5, Here we have 2, and here we have 2, so we'll round to 2 in the end. And we punch this in our calculator, and this equals 74.9947 ... unit milliliters of suspension, and then we'll round it, and that equals 75 milliliters of suspension. This is the last slide for this video,